In this lecture, we will see some practices for writing larger programs using C. As far as we have seen so far, we always wrote our code in a single file, and this is not practical for very large programs running into, say, thousands of lines or millions of lines. So, we will see what is the usual practice for organizing your code when we have larger programs. Okay. So, one of the basic principles is to separate the function prototype declarations from the function definitions. Okay. We have seen that when we have a function, we have two things to do. One is to declare a function, which is just the types involved in the function, and then the definition of the function, which is actually the code of the function. So, one way to structure it, one principle in structuring is that we will separate out the function prototype from the function definition. Now, place all prototype definitions, structure definitions, type defs. So, just the declarations, you will place it in a file with suffix .h. So, right now we have been coding in a file called .c. So, right now what we are proposing is that the declarations alone, we will place it in a separate file with suffix .h. You have already seen such an example, which is stdio.h. We never bothered about what is inside stdio.h. Now, we are talking about how to write these header files. Now, declarations are only half the function, right? I mean, we have to write the definition of the function, the code of the function. The actual code of the function, you place it in a .c file separately. So, for example, list.h contains the definitions of the struct DLL node for doubly linked list and so on, and list.c would contain the bodies of the functions. Now, we will see why separate .h and .c. Programs that use the doubly linked list need to know only the declarations actually. These are think of these programs as the consumers of this code. Now, it does not need to know how the code is implemented, just what to call and what is the declaration of the function. Now, if we do this, then list.c can be compiled separately into object code. So, we can say gcc -c list.c, this will produce just a file called list.o. List.o is not executable, but it can be used in other programs to create executables. Okay. So, how can we do this? This is the procedure known as linking. So, we can link the list.o. So, notice the difference here. When we say gcc -c list.c, what it would produce is a .o function, .o file, and this .o file can be included to produce output. So, this says that we are compiling prog.c file with list.o object file, and the output we will produce is called prog. So, gcc -o prog means the output file we will produce will be called prog. So, if we omit -o prog and we simply say gcc prog.c list.o, then the file that we will get is a.out. If we specify an output file, we will get that output file name. Now, inside prog.c, let us say that we need to use list functions. So, prog.c will include list.h. This is the important thing. It will not say include list.c, it will just say include list.h. This is similar to what we have seen with stdio. We did not bother about whether there was an stdio.c file. We said we will include stdio.h. Also, notice the difference that we are using double quotes instead of angular brackets. So, when we wrote stdio.h, what we had was okay, when we wrote stdio.h, what we had was angular brackets, open angular bracket and close angular bracket. Here we have quotes. Okay, why is that? We will see this. So, what is the advantage of separating list.c from proc.c? Why break it up into multiple files? One advantage is that it saves repeated compilation of list.c functions when compiling proc.c. Okay. So, the double quotes around list.h specifies to the C preprocessor, we will see this in a subsequent lecture, that the current working directory will be searched for list.h file. So, since we are saying that include list.h within double quotes, what it means is that where is list.h found? It will be found in the current directory. If it is not found in the correct directory, it will search for some standard library paths, some standard header file paths. Okay. So, in the case of stdio.h, we put angular brackets around stdio.h. That means that stdio.h will be found not in the current directory, but in some standard library directory and standard header directories. So, when you use double quotes, you can also use some full path name. Suppose your full path name in a Linux system is /users/btech2115/1t/prog/list.h. You can specify the whole path as well. This is a more general notation. So, currently the structure is as follows. You have a list.h file, it has just the prototype declarations. List.c will define those functions. So, first inside list.c you would say include within quotes list.h and then have all the function definitions. Proc.c needs list.c functions, but instead of saying include list.c, it will say include list.h within quotations. Okay. Now, we will see how to compile such a setup. Okay. So, what is the division of work? What is the separation between the .c and the .h files? .h file is the public interface, that if anybody else, any other program wants to use the list functions, what you would do is include the list.h functions, include the list.h file. Now, list.c implements, defines all the functions that list.h has declared. In addition, it can also define other functions, but these functions will not be available to other programs that are using the list.h file. So, files using list.h will not be able to use these extra functions or even know about these functions. These are thought of as private functions. So, this can be used to implement certain details of your code that other users of this program need not know about. So, the general principle is what is known as information hiding or localization. So, the break your programs into modules. We have already seen one way to break a program into modules, which is by writing functions. Now, this is another way to, this is another level of modularization, where you say that take a collection of functions and put them in a file and have multiple files. Now, each module implementing some aspect, for example, a data structure like a linked list. Now, if a module B does not need to know the details of how another module A works, then we do not need to tell B about how it is done, but module B should use module A's .h file, not the .c file. Now, why do we separate definitions into .h and .c? There are some reasons. Programs that use the list functions, for example, are typically consumers, and they do not need to know the exact details behind how these functions work. Okay. And we have already done this in other, we do not know about how scanf or printf worked. We just know that scanf needs these two arguments. For example, it needs a format string and it needs the variable to be printed. The printf needs the format string and the variable to be printed. Similarly, scanf needs a format string and the variable to be assigned. So, we just knew that, we do not know anything about how scanf or printf is actually defined or implemented. We just know that it needs these arguments and therefore, we can call them. So, this is the kind of separation of detail that we are hoping to achieve. Now, so if some program wants to use the list functions, Such programs can use the prototypes using the include command #include within quotes list.h. Okay. So, again to remind, the double quotes specify that it is the current working directory that list.h is present in. You can also give full paths. List.c program will contain all the actual function definitions. Now, usually header files are much smaller than the C files. If list.h and list.c are separated, then list.c can be compiled ahead of time, and you can generate the object file. Okay. Now, notice that list.o in this case will be not executable. It is just an object file that can be used to build executables. Now, list.c program is complete except for a main function. So, it has a lot of functions. It defines all the functions that list.h has declared, plus optionally some more functions, and it can be compiled to produce an object code, but it cannot be done, it cannot be compiled into an executable code because it does not have a main function. Okay. Now, suppose we have written a function called prog.c that uses many of the list functions that uses list.h. Okay, we can compile prog.c to generate an object code gcc -c prog.o prog.c. Okay. So, now we have two object files list.o and prog.o, and then we can use these two object files to create the executable file. Let us look at a diagram which will hopefully be helpful. So, list.h includes prototype declarations, but not the function definitions. List.c defines these functions. So, in order to define these functions, first it says include list.h, therefore, it will get all the declarations, and then it has this code which implements the list function definitions. Prog.c is a consumer which needs these functions. So, how does it do it? It does not say list.c, it says include list.h. Okay. So, the declarations of all the functions are available to prog.c. Now, I separately compile list.c into list.o using gcc -c and prog.c into prog.o using gcc -c. Okay. So, now I have two object files list.o and prog.o, and these will be combined using gcc -o. So, this says that the output file will be called a.out. The compilation units that I need are prog.o and list.o, and so use these two files in order to create the output file a.out. And what is the big advantage here? Let us consider a scene where the prog.c file changes. I need some changes to be made into prog.c. Maybe I add some more functions, modify some functions and all. So, now I need to recompile and produce the output file. I have changed prog.c, but not list.c. Okay. So, let us say prog.c has changed. What should I do now? I should compile only the prog.c. I can say gcc -c prog.c. Now, I will produce a new prog.o file. Okay. Notice list.c has not changed. So, we do not need to recompile list.c. So, we can just say gcc -c prog.c, list.o is the same as before, and then I can use the new prog.o, the old list.o in order to produce the new a.out. So, notice the a.out depends on prog.o and prog.c has changed. So, only this path gets recompiled, which is saving a lot of effort, and in large programs, when one particular file changes and you recompile the project, only the necessary files get recompiled. It does not recompile the whole project, which will take a lot of time. Instead, it will compile only those files which are necessary. So, this is a huge advantage. Okay. So, this just repeats what was said in the last slide. Okay. Now, a couple of thoughts about writing data structure libraries. there is no one design which is best for a data structure library. Choose your structured function, structure functions to be as complete as possible for your programs. Now, programs can be based only on the function prototype. Suppose I write a program which needs a list function, I can just look at the function prototypes in the .h file and then write my program. Consumers do not need to know how the program is implemented, just what the functions are, what are its arguments, not the details about how it is implemented. Now, implementation of libraries should be very sound. All boundary cases should be completely defined and the implementation should thoroughly match the specifications. So, libraries need to be tested and debugged thoroughly before other users can use it. Also, one more thing, allocation and release of storage. If the library is allocating storage, it is only sensible to provide routines in the library itself which can free those storage. Okay. So, it cannot be that library is allocating a storage and the freeing of the storage has to be done outside the library. That is not a sensible design. So, if the library itself is allocating storage, you give library functions to free the storage as well. Okay. For example, in list.h, memory allocation is done only in two places, make empty list and make node. So, to deallocate that, you should provide a free functions for these functions corresponding to these functions.